All right, guys. So far we've been really talking about these functional transforms for Laplace transforms, and we've gone through a variety of them. So hopefully you can actually see how these actually work. There are two more that I'm going to want to derive for you. They're actually going to be done almost simultaneously. Once you end up finding one, you almost automatically end up inheriting the other. I'll show you how that ends up happening. They're the Laplace transform for two very, very common functions. They're the sinusoidal functions, right? So here, this is a continuation on our discussion of functional transforms. And this is example number 4, right? And the problem statement is given f of t is equal to sine of, let's say, omega t. Let's get rid of beta. So the sine of omega t, and find the Laplace transform of f of t. Right. So here, I'm going to go back to the definition, and the Laplace transform of f of t, by definition, is the integral from 0 to infinity of e to the minus st f of t dt. And I'm actually going to just plug in sine omega t. So here, the Laplace transform of sine omega t is the integral from 0 to infinity of e to the minus st times sine omega t dt. Uh, Now, in this particular case, again, I'm sure the book does one very clever thing. I'm going to rederive the Laplace transform of this using a different technique, a different point of view. It's going to lead to the exact same result, plus it's going to give us something extra. So one of the things that I'm going to do here is, just like I had done previously, is I'm going to integrate this by parts. And remember that the integral from here, it's going to be from a to b, the formula for the integration by parts, the integral of u dv is uv evaluated from a to b minus the integral of v du. And we need to pick a u, we need to pick a dv, and it really doesn't actually matter for this one which one you end up picking, but I'm going to go ahead and let u equal sine of omega t, in which case my du, the derivative of sine is cosine, so this is omega times the cosine of omega t dt, where the omega has been brought out because of the chain rule. And if I let my dv be the extra part, well, this is e to the minus st dt, then my v is very simple. It is minus 1 over s e to the minus st, like this. I have all the pieces that I need in order to use this formula here. So here, I'm going to have that the Laplace transform of sine omega t is going to be u times v, which is minus 1 over s sine omega t times e to the minus st, and I'm going to evaluate as t approaches infinity and t equals 0, and then minus the integral from 0 to infinity of v, which is minus 1 over s, e to the minus st, times du, which is omega cosine omega t dt, like this. So there's a lot of stuff that's actually going on here, right? But it's a matter of careful bookkeeping. Once again, I'm going to concentrate, at least initially, on figuring out what this part happens to be, right? And on top of that, the exponential, I'm going to take the denominator. The minus 1 over s is a constant. There are only two places here where the t actually appears. One is in the sign, one is in the exponential. So here, let me rewrite this in the following manner. So here, the Laplace transform of sine omega t is equal to minus 1 over s. And here it is sine of omega t. And I'm going to rewrite this in such a way that here, this is e to the st, like this. And then we have t approaches infinity, and then t is equal to 0. So I'm doing this just to bookkeep. Over on this end, the two minus signs cancel out, and I can pull the omega out of the integral, and I can also pull the s out of the integral. So I'm left with plus omega over s, the integral from 0 to infinity, with e to the minus st times the cosine of omega t dt, like this. Now let's really focus in on this part right here. The sine, it oscillates back and forth between 0 and minus 1 to 1, right? So it oscillates back and forth between 1 and minus 1. Can never get bigger than 1, can never get smaller than 1. However, the exponential, it's always going to tend towards infinity, and that's the one that's in the denominator. So that first limit, as t approaches infinity, it's going to tend towards 0, right? It's just going to disappear. The other one, we can just plug in 0 directly. So here, what we have is the Laplace transform of sine omega t is equal to minus 1 over s. Well, that limit is 0 minus sine of omega times 0 times e to the s times 0. Well, sine of omega times 0, well, that is 0 divided by e to the s times 0, well, that's 1. So this whole first part, by our arguments, this whole thing, it disappears. And what we're actually left with is omega s, like this, 0 to infinity, e to the minus st times cosine omega t dt. Now, one thing that we did previously was we recognized a Laplace transform when it came into one of our equations. And I'm calling on you to do the same thing. So let's actually write this out a little bit more cleanly as well. So we have the Laplace transform of sine of omega t. Well, the first term goes to 0, and then we're left with omega over s, integral from 0 to infinity of e to the minus st times the cosine of omega t dt. This right here, right, has the same mathematical form of a Laplace transform, except now, rather than being the Laplace transform of sine omega t, this is the Laplace transform of cosine omega t. So in terms of the notation that we've been using up until now, one of the things that we can say is that this is omega over s, the Laplace transform of cosine omega t, like this. So I'm going to keep this result in my back pocket, right? So this is going to be the result, which is going to be used later on. And the result is that the Laplace transform of sine omega t is equal to omega over s times the Laplace transform of cosine times omega t, and I'll keep this under my belt. But we want to keep on working with this. We can't just leave it at that. We know that now one is written in terms of the other. So one of the things that we can keep on doing is we can keep on integrating what we're actually left with when we go back to our definition. We can integrate that by parts again. So this right here, we're going to integrate by parts. And we're going to choose essentially same u and dv that we actually had previously. So here, I'm going to let u equal, what we've done was the sinusoid. So here it's going to be cosine of omega t, which means that my du is going to be minus omega sine omega t dt. My dv was the other part, which is e to the minus st dt. And the integral of that, well, it's minus 1 over s e to the minus st, like this. Which means that, again, by integrating by parts, one of the things that we can do is we can rewrite this as the Laplace transform of sine omega t is equal to omega over s, like this. And it's u v. So here it is cosine omega t times minus 1 over s e to the minus st. And I'm going to evaluate as t approaches infinity and t is equal to 0. Approaching 0. Let's let it equal 0. And then minus the integral from 0 to infinity of uv du. So here we have uh, minus 1 over s e to the minus st times minus omega sine omega t dt. And I have to be careful. I have to put all of that in parentheses. Now, there are a few things that, again, we can do to simplify things. So this whole thing I can rewrite in the following manner. We have the Laplace integral, Laplace transform of sine omega t is equal to omega s on the outside. We're going to have minus cosine omega t s e to the minus st. And we're going to evaluate as t approaches infinity and t approaches 0. And then we have 3 minus signs there, so they're going to be minus signs like that. And we have omega over s that we can pull out of this integral. So we have that part that we can pull out. And then we're left with the integral from 0 to infinity of e to the minus st sine omega t dt, like so. Now, as we concentrate on this and focus in on that, we still need to focus in on this portion right here. Once again, actually, I did make a mistake with this. Be careful. I did bring the exponential down to the denominator, so rather than it being negative, the exponential, it should be a positive one. So this is quite literally coming from here. When I promote it or demote it to the denominator, it loses its minus sign. And the same argument holds for at least that first term that we actually had previously. Remember, the cosine, as t approaches infinity, it oscillates back and forth between a maximum of 1 and a minimum of minus 1. However, the exponential e to the minus st as t approaches infinity, it approaches infinity. So that first term in that limit does approach 0. However, we actually have to be very careful with the second term, right? Where we plug in t equals 0. So here, what we actually have is we have omega s, we have minus 1 over s coming from that term. And we have 0 minus the cosine of omega times 0 times e to the s times 0. Now, notice that this term does not disappear. It does not go away, right? That's actually going to be important. The cosine of 0 is 1. E to the 0 is 1. So we have 0 minus 1 there. And then we actually have minus omega over s, the integral from 0 to infinity of e to minus st sine omega t dt, like this. And let's go ahead and clean this up. So the Laplace transform of sine omega t like this is that nasty mess. This term here turns into 1. So it's 0 minus 1. So we can rewrite this as the Laplace transform of sine omega t is omega over s. We have minus 1 over s, 0 minus 1, minus omega over s. And if you take a look at what we actually have here in this integral there, that is once again the Laplace transform of sine omega t. So we can rewrite it as the Laplace transform of sine omega t like this. Notice that one of the things that we actually have here now, even though it looks kind of nasty, and it is nasty. In fact, let me go ahead and simplify this equation just a little bit. One of the things that I can do is I can actually multiply both sides here by s divided by omega to move it to the opposite side. So here we have s over omega, the Laplace transform of sine omega t. And here, this minus 1, that minus 1 cancel out, and we're left with 1 over s minus omega s, the Laplace transform of sine omega t, like this. This right here is an algebraic equation that you can actually use to solve for the Laplace transform of sine omega t, right? In fact, one of the things that, again, we can do to simplify this a little bit is I can multiply both sides by s, in which case I get s squared over omega, the Laplace transform of sine omega t, like this. On this side, I end up with 1. Here I have minus omega, the Laplace transform of sine omega t. And if I add this to the opposite side, let me write that again. So minus omega cross transform of sine omega t. If I add this to the opposite side, I can then factor it out. So here I have s squared omega, Laplace transform sine omega t is equal to plus omega Laplace transform of sine omega t, and that's equal to 1. I can actually factor out the Laplace transform of sine omega t. When I do that from the first term, I end up with s squared over omega plus omega, and that's equal to 1. And I can, this is gross, but it'll come out. Sine omega t is 1 divided by s squared over omega plus omega, like this. Now, I don't like fractions within fractions particularly, so one of the things that I can do to simplify is I can multiply numerator and denominator by omega. In the numerator, I end up with omega. But here, I actually have to distribute this omega to both of these terms. And what I end up with is s squared plus omega squared. So my final result, and this is the final result, is that the Laplace transform of sine omega t, and I'm so thankful that I got it right. You can check your book. There are multiple ways in which you can do that. Is omega divided by s squared plus omega squared. And this was one of the things that we were actually looking for. Now, that takes care of the Laplace transform that we were actually looking for. One of the things that I mentioned previously is that we're going to get the cosine one almost for free. And it's because of a relationship that we had worked out previously. It's this relationship right there, right? So I'm going to go ahead and write that relationship down at the very bottom. And you'll see how the freebie works. So we had the Laplace transform of sine omega t was Laplace transform of cosine omega t. And I need to make sure that I get the coefficients right. So it's omega divided by s. It's a multiplicative factor. So here in this equation, which we'd found previously, I can solve for this. So L cosine omega t is equal to s over omega, the Laplace transform of sine omega t. But Laplace transform of sine omega t we found was omega s squared plus omega squared. Now take a look at the beauty here. This omega, that omega cancel out. That s comes along for the ride. So the Laplace transform of cosine omega t is equal now to s divided by s squared plus omega squared. This was another major result that we almost get for free. We've now have quite a bit of experience in calculating some of these Laplace transforms. We will start taking a look at now more operational transforms as well as some major results from tables. I'm not going to be able to do all of the Laplace transforms for you. Luckily, we don't have to reinvent the wheel every single time. There are some that are already tabulated, but hopefully you get a little bit more comfortable in working with these concepts and these ideas.